In this chapter, we are going to be talking about transition metal complexes and coordination chemistry. And this is a third type of compound that is part ionic in character because of the ions involved and their charges. And it's also part covalent in character. So this is actually discussed in a Chem 111 video. So if you want to remind yourself of that, Chapter 2, it's about a 5-minute video, number 9 on that playlist. And it says 2 types of chemical compounds, ionic and covalent. But this is actually a picture of a covalent compound. We don't see all the carbons and hydrogens here. But covalent, remember, means sharing electrons so that every atom is happy and gets 8 electrons around it. So that type of compound, a covalent, is nonmetal only. And again, sharing electrons, I'll just draw carbon dioxide really quick, so that everything gets 8. Or water, remember water is bent. So covalent compounds have very specific shapes, and we have discussed very small covalent compounds. Ionic compounds, recall, are when a nonmetal, like chlorine, a chlorine atom, steals an electron from a metal. So an ionic compound is no sharing of electrons. This is the nonmetal stealing electrons. And in order for a compound to exist, those charges have to cancel to 0. So sodium chloride's formula is written without the charges. There are no shapes associated with an ionic compound, but rather all of those are solid. And the charges balance in the formula so that the entire compound is neutral. And the ratio of colored marbles, so to speak, depends on the ratio of the ions. Magnesium chloride exists because magnesium is a +2. So magnesium's charge of +2 requires 2 chloride ions. So this is not magnesium covalently bonded to a chlorine gas molecule, but again, for an ionic compound, the charges cancel to 0. So we'll see that in this next type of compound, it has both properties of covalent, meaning that there are specific geometries, and the central metal in this type of compound is a positively charged metal. And then a new word that we're going to learn is ligand. So we say that the ligand coordinates the metal. So the ligand is either an ion or a neutral molecule with lone pairs. So we'll take a look at that in a minute. But a ligand coordinates the metal. That's what we say. And that's where the term coordination compounds probably is associated with. And we're going to think of the lone pairs as teeth. So the teeth serve to bind, bind the metal, so to speak. And so the term bidentate, in this case, bi means 2. There's bidentate, there's 2 sets of, and I'm going to put teeth in quotes because, of course, they're not really teeth, but anything that has a negative charge, like a pair of electrons, will be attracted to this metal ion that's in solution. So we're considering iron +2 in the aqueous form. So many iron 2 complexes are soluble. So in solution, a free metal cation might be coordinated by ligands if there are lone pairs on the ligand, or if the ligand is in fact a negative polyatomic ion. So we're going to draw this compound as though it were coordinating the iron center in just a minute. So monodentate ligands, I'm going to list a few. That means one tooth. Oh yeah, I already put the D. So some common monodentate ligands would be water. Remember, water has 2 lone pairs of electrons around it. So the lone pairs on the oxygen will be just like lone pairs on nitrogen and be attracted to that metal cation. Ammonia, NH3, that's our weak base that we spent a great deal of time discussing. Ammonia, or any amine group, almost all the time, we'll find that nitrogen has a lone pair because of its position on the periodic table. So nitrogen has 5 valence electrons around it. So it's very happy to have 3 bonds to it and retain its lone pair. So that's very common. Ethylene diamine is carbon with hydrogens around it. Oops, I drew that the wrong way. The amine group was on the end. We could have a nitrogen, I'm going to put the H's here, bonded directly to a carbon and another carbon. So it appears that the right 3-dimensional size and shape of the bidentate ligands is where there's 2 carbons in between the nitrogen groups, or they don't have to be nitrogen, but the donor atom, as we call it. So if we look at orthophenanthroline, and remember that every corner is a carbon, this is the right size to actually wrap itself around this metal. So this is called ethylene diamine. I think ene, di, meaning 2 nitrogen groups. So that's abbreviated EN. So these monodentate ligands are neutral. That means they do not have a charge. They are just neutral covalent compounds. But because of the lone pairs and the size, if we have a longer molecule, those lone pairs will be attracted to the metal. There are also anions that serve as monodentate ligands, and one of those is nitrite, NO2 with a -1, or a chloride ion, or a fluoride ion. Apologize for the shadow here. Cyanide is a common polyatomic ion, so if we drew cyanide's dot structure, it also has a nitrogen with a lone pair and a carbon with a lone pair. So it would be a good idea if you were my student preparing for a test to know the polyatomic ions and their charges, and also to be able to recognize a neutral ligand, because that is going to serve to help us figure out the charge on a metal if it's unknown. So what we're going to do here, and this is done commonly for biology, when there are large molecules, we don't want to draw everything. We may represent the rest of the molecule with a ribbon. So we've seen this for proteins and DNA and so forth. So what I'm going to do is take this orthophenanthroline ligand and draw it as though it was coordinating the metal. So because the nitrogen's lone pair is actually what is attracted to the metal, I'm going to show that right at the coordinating sites of an octahedral geometry. So that would be one ligand and then a second orthophenanthroline molecule could wrap itself around as such, and then a third molecule. I'm going to put the nitrogens in first. And so what we call this, when the metal is surrounded by ligands, we call this entire group here, this is the coordination sphere. So there's a bit of vocabulary in this chapter. And we could also write this as a formula, and when we do that, we show these type of brackets, and we would write Fe without the charge. Man. It's a toss-up between which overhead light to use to see this. We would show the iron, and then O-fin is an abbreviation for that ligand, and there are 3 of them. And then the charge on the ion, since the orthophenanthroline ligand, that is what we're calling O-fin. It's a neutral molecule, so it does not have a charge, meaning the metal complex ion has the same charge as the central metal. So this here would be called the complex ion because it has a charge, and complex meaning this is actually the complex, not complicated complex, but like an apartment complex, I suppose. So this is the complex ion, and we might see this, there we go, I'm just trying to get that shadow off of there. So this ion could be shown just as the separate ion, just like we could show sodium as an ion, or we could show sodium's formula in a neutral compound without the charges. So since this is a +2 ion, it is possible, and this whole thing is still dissolved, would be dissolved in solution. We could neutralize this charge by having, for example, 2 chlorides here. So the formulas in this chapter are going to be very strange, and if we remember that what is inside the brackets in the formula is describing the metal with ligands around it, and then anything outside the brackets would serve to cause that entire compound to be equal to 0. So if we saw the entire formula, that Cl2 means there are 2 chloride ions also in solution, so that this entire formula's charge cancels to 0. One other vocabulary word I want to mention here, if we stay looking at this picture, we would say that the coordination number of the Fe complex here would equal 6. So the coordination number is the number of sites around the metal. And we are going to see a coordination number most commonly of 6 and sometimes 4. So since this octahedral geometry, that is back in a chapter 9 Chem 111 video if you want to look back in your book. But the octahedron is shaped out of geometry that we would get. And so the coordination number is how many sites that the metal is coordinated with. And that may not be the same number as the number of ligands around it. So in this case, there were only 3 ligands around it, but each ligand, the orthophenanthroline ligand, coordinates the metal in 2 places. So we'll be talking about the coordination number of the metal. We will also be talking about the oxidation number. So that is generally the charge. So the oxidation number of the metal, in this case, is +2 because we had iron +2. And then the oxidation number of the ion is also the same. And that is not always the case. I'm going to draw one more example where we have chlorides or cyanides around the metal as a ligand. And in that case, the oxidation number of the complex will be different from the oxidation of the metal. So the oxidation number of the, I'll put this here, I'll put the entire formula here, but the oxidation of the complex itself is also +2. And again, that's because the orthophenanthroline ligand is a neutral molecule. So we could have the exact same formula, and let's say, for example, that waters, which are neutral, coordinated that metal. So in that case, if we tried to draw that really quickly, we would have 6 monodentate ligands, or 6 waters around the ion, and then the chlorides out here just serve to keep the entire charge of the compound equal to 0. So if we were to draw that complex over here, we put iron in the middle. And let's say we did not know the charge on the iron. And the way we would figure that out is the anions. So if I put, I'm going to show the oxygen actually coordinating the metal because the lone pairs on the oxygen are attracted to this plus. And we're going to figure that out even though we know it already. So when a metal is in coordination chemistry, the ligands actually change the properties of the metal, and so we'll discuss that more in detail. So this is the metal complex, which is abbreviated or shown as the formula inside the brackets. That's very important. So this entire complex, because there's 2 chloride ions here, we know that the entire complex has to be a +2 because each chloride is a -1. And again, that means chloride, a fabulous spectator ion, is outside of that coordination sphere. So since the entire complex has to be a +2 so that these charges cancel to 0, and most importantly, water is neutral, we know that the charge on the iron must also be a +2. So in the next few slides, I'll show several different formulas, and we'll see that sometimes the entire complex has a negative charge, in which case we would have metal cations over here.